Hi guys, today we're going to go over some basics behind friction so you could complete some assignments throughout the end of this week dealing with it. So we've been on forces. We've seen friction come up in some free body diagrams that we had to draw. We should probably already know it happens when surfaces are in contact with one another. But there's some more specifics to friction other than just that. Number one, there's two types of friction, and comes in two forms: static friction and kinetic friction. And just to define these briefly, and we'll explain more here in a second with some simulations to look at. Static friction we consider non-sliding friction. There's no sliding going on. There could be moving. You could have something like a wheel of a car going on the road that's moving, but it's not sliding on the road. So static friction is non-sliding. Kinetic friction, therefore, is when we do have sliding occurring between two surfaces. Whether we're talking about static or kinetic friction, what makes up both of these kind of frictions, what makes it bigger or smaller, the amount of it, depends on two factors. And one of those two factors is called the coefficient of friction. And we often symbolize the coefficient of friction as it looks kind of like a cursive U, but actually that's a Greek letter mu, and it represents the coefficient of friction. Now, what does that exactly mean? It means really a value, a numerical value that is based on the roughness or smoothness of the surfaces in contact when dealing with figuring out friction and how much there is. All right. Usually this value is between 0 and 1. All right. So usually it's like a decimal value, point something. Where if it's closer to 1, this means the two surfaces in contact are rough, and the closer it is to 0, it means they're more smooth. And it's one of the rare values that we come across that have no units. And one of the reasons why, without getting too mathematical here, is because think of it like a scaled value. Like let's say on a scale of 0 to 1, how rough or smooth are two surfaces when they're in contact. All right, so that's more like an idea of on a scaled value, okay, not a physical unit like we're used to, okay. But just realize that the coefficient of friction is really only part of what makes up friction. All right, and another thing worth noting, that depending on what type of friction we're dealing with, static or kinetic, the mu value, coefficient of friction, is always higher in its static form as opposed to its kinetic form. Let me give you an example here, since we're going to be dealing with like some stuff with braking systems as examples here coming up soon, and you'll have a How Stuff Works about it later in the week. Let's take one surface being a typical car tire and the other surface being the road, asphalt. All right, so this examples are going to be for tires, rubber tires on the road. And when your vehicle's tires are not sliding, the mu value is approximately 0.8 for dry tires on dry road. It could vary a little bit because, of course, there's different styles of tires, but on average, it's about 0.8. And that's good because remember, we said a moment ago that these values range between 0 and 1. And the closer we are to 1, the better if our goal is to have more friction involved, right? So 0.8 is obviously much closer to 1 than it is to 0. However, when we get sliding on a road, hopefully you don't, but if you do, if your tires start to slide, now the mu kinetic, the coefficient of friction when you're sliding, drops down to 0.65. And again, this is part of what makes up the overall force of friction. We'll get to the other part in a second. So that might not seem like a drastic difference, but it really is when you think that the scale range is roughly from 0 to 1. And I say roughly because there are some extreme cases of friction which can be over 1, but typically these values are between 0 and 1. And if that's the way things typically are, that's a 15% drop in your coefficient of friction, which in turn is going to create a 15% drop in your overall force of friction if you're sliding under kinetic circumstances as opposed to being in more safe static values. I mean, I think we all know by common sense you would probably rather have your car not slide to a stop when you hit the brakes, right? And this is actually the science behind anti-lock brakes, we'll talk about more later. So there's just a specific example of that. If you want more friction, you want to be under static conditions as opposed to kinetic conditions, because the mu coefficient of friction, the roughness or smoothness between them, stays higher when it's static conditions. All right, so let's see what else is going on with friction. Remember that mu is the part of what makes it up, either type of friction. The other part is another force we're familiar with, the normal force. Don't forget the normal force is a force we've dealt with before, and it's when a surface pushes back against something else. So if we draw a free body diagram of something being pushed along, let's say we have an applied force this way, hence we have friction in the other direction. And let's say we are sliding, so we're going to call our friction kinetic friction. So we'll put an extra subscript K there. But while this is going on some surface, there's also weight down and normal force up. And we've learned this before. And remember, the normal force is a surface pushing back on the object. And the size of that normal force creates pressure between the surface, two surfaces in contact. And that's the secondary factor with how much friction is involved in the situation. So if you want a high amount of friction, you want your coefficient of friction, the number between 0 and 1, you want that to be high, and also you want your normal force to be high. And it does turn out in many cases, normal force does equal your weight. So if you have a 100 Newton object, that is also your normal force. So why don't we say weight is the other factor? Well, I'll tell you why, without getting too complicated. When we get to more complex scenarios, like if the applied force is at an angle, that changes the normal force, but it doesn't change the weight. Because if I pull at an angle upward, I alleviate some of the weight off the floor, and the floor doesn't have to push back as hard. So if we said the weight always equals the normal force, that wouldn't be true. There's a variety of other circumstances like that, which also would be a problem. So yes, in many cases we studied normal force equals a weight, but it doesn't always have to be that way. So normal force, though, is always what's causing the pressure between the two surfaces and how much they're pushing together there is. Therefore, if you want friction to be extra high, you want these to be high. Let's go back to the car example, right, of tires. So we already said it's better to be under static conditions as opposed to kinetic conditions, right? Non-sliding static conditions, because that 0.8 is a higher value to give you a higher amount of friction. But it also is more helpful, not just solely on that, is to have more normal force. How can we do that? Well, we can increase weight, and weight will increase the normal force. Maybe not at a 1-to-1 ratio, but it definitely will increase it. So for this reason is one of several reasons why really all vehicles are front-wheel drive nowadays, if they're not all or four-wheel drive. Because the engine in most in the overwhelming majority of front-wheel drive cars sits on the front end of the vehicle, which are the drive wheels, right? So there's a lot of downward force from the weight, because more is distributed in the front where the engine is, on your drive wheels, creating a higher normal force above your wheels to give you more friction, hence more traction, basically. Whereas years ago, when most vehicles were rear-wheel drive, then in most of those vehicles, not all, but most, there's just a trunk back here, an open trunk, not a lot of weight right on top of it. And what people used to do with rear-wheel drive vehicles to gain more traction, especially in the winter, is to put like sandbags or something heavy in the trunk so it pushed over them, so there was a bigger downward force, and therefore again the upward normal force would have to be greater, pushing the wheels together with the road. All right, but it's not just one of these two things that make up friction, it's both of them. And it's pretty simple. If you want to write it as a formula, kinetic friction, that's the sliding kind, is equal to mu kinetic times the normal force. And static friction at its maximum, we'll discuss that a little bit more in a second, is equal to mu static times its normal force. All right, so that's pretty much, in a very quick overview, the deal with the different types of friction and what makes it up. And also, one other important thing is friction is always an opposing force. Whatever way something is sliding or trying to slide, it opposes that. So in our free body diagram up here, if my applied force is trying to slide to the right, friction opposes that and goes to the left. That's always true about friction as well. All right, now I'm going to flip over to a simulation, two actually. The first one is actually going down even further and looking a little bit deeper on why friction exists. And in this animation, simulated animation, we have two books sitting on top of one another. And what I could do with the top chemistry book is I can move it side to side. Okay? I can pick it up a little bit. Now it doesn't look down below down here like I picked it up. But this blown up view is like the microscopic view, if we could see that. And before I say anything more about that, we should say that even surfaces that feel pretty smooth to us, like maybe your cover of your textbook or the surface of a desk or something like that, feels pretty smooth, right? But microscopically, there's a lot of little bumps between them, okay? Or that make up that surface, even if it feels smooth to the touch. And remember what we said, the two factors that make up friction, and this will make it really make sense why those are the two factors that make up the force of friction, is the roughness or smoothness between the two surfaces. We called that the coefficient of friction a moment ago, that symbol mu that looks like a U, right? And basically, the more bumps that could possibly lock together, the higher the mu value is going to be. All right, that just kind of makes sense. And also how hard they're pressed together, right? Through that normal force we talked about. But notice one thing here, and there's a little thermometer temperature to the right. And we all probably know a feature about friction, because if we rub your hands together, it makes heat, right? Now we're not going to focus on that aspect, but it's important for this simulation to look at. So this is the resting heat temperature of the thermometer. So if I just set the chemistry book on top of the physics book and don't at least try to move it, there's still no friction. So if something is setting on a surface and no force is trying to move it side to side with the other surface it is in contact with, then there is no friction. Yes, there's bumps, but those bumps aren't trying to move across one another, so there's no friction. But once I start sliding them and there's a normal force pressure between those bumps, you can see the thermometer starts to rise, creating heat. And the main reason why it does create heat, these particles start to vibrate like crazy, and that vibration causes one to hit the other, to hit the other, to hit the other, and then that gives off excessive heat. But that's the main theory behind why these are the two factors, mu and normal force, coefficient of friction and normal force, that creates friction and makes it bigger or smaller. So let's go to another example with another simulation. We talked about the two types of friction, static and kinetic. So right now on this box, this man is not pushing on the box. There's no force trying to make this box move along the surface. So therefore there is no friction right now. But notice once I start making this guy push, now that there's applied force, immediately there's a frictional force. All right. Right now this man is not pushing hard enough to make this box move. But he's trying to, and that makes there a friction. You can see pointing to the left, there is a red friction arrow opposite of my applied force, which if you look below, the applied force is about 281.75 newtons. Okay? So right now we would call this static friction because it's not sliding. But if I push harder and harder and harder, static friction grows and grows and grows. Remember in that little formula a minute ago, we wrote the formula for its max static friction? Its max static friction occurs at the breaking point. So right down here, since I could vary this, my applied force, and the static frictional force varies with it a lot, we're not at its maximum. It's not on the breaking point of moving yet. So if we ever use that equality formula, FF static equals mu times normal force, to find static friction is only good at its max. Whereas its max, it's at its breaking point. So if I slowly increase it, eventually I'll find a place where this thing breaks into motion. Still not, still not, still not, and very soon it will. Right there about was its breaking point. It was close to 490 newtons. Okay, but once it breaks into motion and slides, now we're under, there's still friction, but now it's kinetic friction since we're sliding. And you can notice down here is very small, but that gives you the mu values for this crate. Remember the mu values, coefficients of frictions, are solely dependent on the textures of the box and the surface themselves. So mu static is 0.5, which is moderate. That's right in the middle of 0 and 1, the typical range, right? But once we begin to slide, it drops to 0.3, and that's what we talked about before, why it's, if you want more friction, if that's your goal, like with tires on a road, you want your mu to be higher, as high as possible, and it's only to be able to be as high as possible if it's under static conditions, because you can see it drops when you start to slide to kinetic conditions from 0.5 down to 0.3, which is much closer to 0. If I took some other objects here that have different mu values, let's see my options here. Actually, these are all quite similar. But the textbook has different mu's and a whole different mass, so it's much easier to get a textbook into motion. All right? I don't have to put it up to almost 500 newtons to get this thing into motion. And that should make sense, because there's a lower mu. But even though there wasn't, the textbook has less weight, therefore less normal force. And normal force, we said, was also one of the things that makes up the overall force of friction. So now let's get to a little quick, less than 1 minute video we'll watch embedded right now in my own video here about anti-lock brakes. And I'll do a little small discussion after that, and then later in this week for How Stuff Works, you're going to read more closely about anti-lock brakes and why pretty much all modern vehicles now have them compared to maybe vehicles of 30 plus years ago, which not all did.
Driver fully applies the brakes in a vehicle without the anti-lock brake system, the brakes can lock. This causes the wheels to stop turning, which makes the tires skid. Skidding tires have very little grip and are not effective at stopping or turning the vehicle, so the driver may be unable to take evasive action. With ABS, when the driver fully applies the brakes, the system uses sensors to detect any brake lockup and rapidly pulses that brake to prevent it from locking. This helps to prevent skidding so the tires can maintain grip. It also helps to allow the vehicle to be steered around obstacles while braking. One way to think of ABS is allows braking and steering. When the driver fully
Okay, so after watching that video once with hearing just the audio of it, I'm now going to mute it, and replay it since it's short, and pause and expand on some of the things we just saw in there. All right, number one, not everybody knows as much as others about vehicles and parts of them, so I'll explain this as if everybody knows nothing about a braking system. All right, behind your wheel, behind your rim, attached to your wheel, is a rotor. It's often a shiny disc that you might notice if your rims have big enough gaps in them to see, but it also might be kind of rusty looking as well if they're well worn and well used for a while. But also, if you notice that disc, somewhere on it is what's called a brake caliper. All right, it's just almost looks like a partial arc along this disc. That's what actually stops you. All right, this is the outside encasing. You can't see the brake pad within it, but the pad clamps on to your rotor, which is this right here, and it's attached to your wheels, and that's what stops you down, slows you down. When you push your brake, a system that's usually a hydraulic system puts pressure on the brake pad and clamps it on this rotor to slow you down. And there's a lot of friction just in that process. This is why you need brake pads fairly often, because those brake pads wear out fairly quickly on this rotor. And if they're pretty worn, it won't be able to clamp on as well to slow you down. But the friction we're going to focus on the most with anti-lock brakes is the friction between the tires and your road. Remember, we want to maintain static, non-sliding conditions, not just for more friction, but for better control, as the video said. If you're sliding, you also could easily go out of control. So that's another bad point of being under kinetic if you're driving. But anyways, in older vehicles, when you apply the brakes for your pedal, this brake pad would just clamp on and stay locked. And if you're going at a decent speed, and especially if it's wet or icy, but even if it's not, it could happen if you slam them on quick enough going fast enough, it will just lock up like it says right here in the video. And that could cause you to lose control and have less friction and more likely to get in an accident. And I'm going to let it play a little bit. With anti-lock brakes, even if you press and hold in the brake pedal, it has a system that automatically pumps the brakes for you. See the pulsing on the brake pad, the caliper there? That represents that it's intermittently locking on and letting go, locking on, letting go, only for brief moments. That will help resist. It's no guarantee, but that will have you resist slide. Trust me, you could still slide during these intermittent pulses, especially if you're going way too fast and there's bad weather conditions. So this prevents brake lockups, like it says down here. It's no guarantee, but it's much better than it was, because anybody older, probably most of your parents, would know that when they probably started to drive and you learned to drive, whoever taught you would tell you, make sure if you're in a quick braking scenario to pump your brakes so you don't slide. And that was true pre-anti-lock brake systems, because if before anti-lock brake systems existed, then you'd have to manually do it. And here was the problem with that. How many people are going to remember to manually pump their brakes when they're about to get in an accident? Most people freeze up themselves and just slam on that brake and it would lock up. So engineers, scientists eventually figured, you know what, we need to find a system that does this for us, hence the anti-lock brake system. Okay. And another thing, you probably felt this, all you that drive, is if you ever especially gently apply the brakes, you could almost feel your brake pedal pumping back on your foot, because that's the feeling of the system occurring intermittently on your wheels. And there's some more complexity than that, but that's the main idea for anti-lock brake systems, keeping you under static conditions to have higher friction and better control and be able to stop quicker and avoid a bad scenario, as opposed to locking up, sliding, being out of control, and sliding itself provides less friction and would take you longer to stop even if you were still in control. All right, so hopefully this all helps us in our ideas, introductory ideas to friction. There's a small worksheet provided today that you should answer a few questions on. Note the directions. I only want you to go through questions 1 through 4 only. Okay, it won't take you long. Anything else on it gets a little more mathematical than I want to get right now. And there'll be some more on this stuff later in the week, especially how stuff works on Friday.